So hello and welcome. My name is Budapest, who doesn't know me, and with my co-organizer Jigsaw Puzzle, we are trying to keep the spirit alive of the Deep Learning Reading Seminar, even during winter times and COVID. My kind of role here is to do a tidbit of short summary of the history of how we got here, in the sense of what was it like before COVID, under COVID, and what are the perspectives. So I will assure you not to take too much of your life. I only do some 5 minutes of the talk, and then afterwards we will start with Gergő, who will present for us some rumblings and mumblings about his favorite topic, which is representation learning. So everyone needs a mini AI life. He does that, and that's it. And even remotely joined, we will be joined by Balázs, who is doing physics in the hardcore sense, so not just in theory, but also in lab experiments, and his field is currently converging to, or he's peaking into quantum computation and quantum machine learning, so that will be the second topic of the day. But let's go ahead.
I imagine that online is safer if somebody is doing like real-life quantum physics experiments.
Absolutely, absolutely.
Maybe he's here also.
No. Yeah, no, also here, but also at home. That's a good point. I mean, he's somewhere here with a probability. That's cool. That's very cool. We can confront him with the question of how probabilities that he sits here. That's pretty okay. So, yeah, we are already kind of, I think, known by many of you. Just as a tidbit of background, we are kind of co-parties in crime in many sense. In the sense of we created together some podcast that's called Machine Learning Cafe. We took over this deep learning paper reading seminar from Devil, the famous Devil, the Graphical, who knows him. We took it over, I think, in 2018, and we were the hosts for the kind of infamous year of 2019 up until it was possible. What we do is my personal background. I'm originally a programmer that did a small tidbit of a detour to become a Buddhist theologian, because why not? That's just fun. And then I went back to do AI research related things. Specifically, I did financial model, time series modeling with some evolutionary computation and also some neural computation. Then I founded my startup Analogy, which was focused on NLP, and I was focusing together with some dear colleagues of mine from that time on delivering knowledge management software to bigger organizations. And afterwards, when I quit, I became what I am now, kind of a speaker for everything. I teach at Frankfurt School of Finance and Management and at University Paris. And also somewhere here in Hungary, Field Academy and other places. But when I'm not speaking, I'm trying to listen as a consultant and as a field consultant out in machine learning projects together with the unsurprising sponsor of today's event, which is Neuron Solution, which is a boutique consultancy and machine learning delivery firm that we grounded or founded together. I will talk a tidbit about that, but that's just superficially. Can you please give also 2 words about yourself?
Yeah, two words, big data and ML expert. and community organization.
And that's it.
So just really in 2 sentences, I'm really enthusiastic about machine learning, so that's why we took over this meetup, like saving no energy with this really since 2018. Sadly, there was this pandemic. Anyway, so I'm doing software development since 16 years, and in the last 8 years I'm in machine learning field and also big data. I also teach sometimes mainly big data related stuff with Spark, but also sometimes machine learning. And yeah, that's all.
Cool. So, good old days. Last meetup, I just really went back to the archive, the all-knowing archive of meetup.com to check where we were. So we last met at the 12th December 2019. There was way more pizza than now. And by the way, we learned our lesson because 94 people said that they will come and only 40 came, so everyone was bombarded with pizza by people like, hey, son, take it at home, and that's good for you. You don't like pizza and whatnot. Oh God in heaven, so sorry about the pizza situation, it is a predictive problem in itself. Anyhow, so the meetup group was kind of kept alive. It's high and healthy, so we have 1,000 members. Though the activity can be increased or should be increased, but we had kind of a bi-monthly,
like
quarterly or 2-monthly meetup sessions where people presented some paper ideas on research or some reading some other papers and then summarizing it. That was before the big winter, and winter was coming, as we all know. We braced ourselves, and while bracing ourselves, I had some good friends in Frankfurt data science who had some good friends in Vienna data science who had some good friends in Barcelona data science who had some good friends in whatever. You know, this is how ideas spread and not just diseases. So all in all, what we created was called Cross Europe, and Cross Europe was a webinar series that was trying to keep alive the spirit of people boxed into their own homes, and we had this new format. Instead of doing meetups, it was kind of a webinar delivered by some people. It was all in all 20 webinars that we did. All the communities contributed, so some people from Bratislava, some people from Barcelona, and this is still a format that is alive. So it's not just, I think, it's not just kept us alive as a meetup community, but also I think it's a new platform that we endeavor to keep it up. So in fact, in next month, there will be, again, a new Cross Europe. So Cross Europe is a format that keeps the spirit, or kept the spirit, but we do believe that meetup format, as in personal, sitting here, eating pizza, eating other people's pizza, you know, and doing some networking is I think in itself worth it. So next up, we will keep up the webinar format, but we will stick to this physical format again. That's the message here. So there are the perspectives. The new spring is coming. I'm talking about this in autumn, so I'm totally not in time serious, you know, whatever. The whole today's endeavor was a bit pushed by our great colleagues at Neuron Solutions, in the sense of they said, like, look, we can help you in this, because we were just like, we should restart the meetup. Yeah, we should. Yeah. It's so cool. Yeah, you do it. Now you send the emails, and so on. So very big thanks to Neuron Solutions as being the sponsor of this event, putting in some physical effort in these things, also not just emotional and financial support. 2 words about Neuron Solutions, just to entertain you a tidbit, is that it's as said, it's a boutique consultancy firm, so we wanted to first and foremost specialize in delivering AI solutions. Then we tried, and then the customers didn't understand what an AI solution is. Okay. Then we delivered some consultancy, you know, an AI solution is, but it didn't work. So we have started doing teaching. And that's why we do 3 things in all together. So we are doing specifically machine learning related courses, technical and business courses for companies, to enable us to work as a consultant, to enable us to deliver some projects. There you see the project. We had some nice projects in pharmaceutical industry, doing Alzheimer-related time series modeling on EEGs of rodents, as far as I remember. So you can ask about that from Gabby. He was working a lot on that. We are currently doing some industry-related computer vision problems, as well as some natural language-related generative problems for media. So we are kind of into many of these fields. Okay, with that, what's the perspective? What we would like to continue as a community? There are 3 community tools that we would like to, Slack is a community tool also. But anyhow, so we have 3 community tools that we would like to keep up / reinvigorate / operate. One is a general Facebook outreach page, which is called Budapest.ai. It's just about spreading the word very generally, using AI, not specifically research-related stuff, but it's kind of a community presence channel. The other thing that we are doing here is, very unsurprisingly, the meetup that we would like to keep up. And the goal of the meetup is to build the community's relationships, so please feel free to socialize with each and every one of you, and also please try to come up with any ideas. If you have it in your heart that you want to present your favorite topic, then don't hesitate to contact us. We can absolutely share this floor with you. We would love to do that. And also there is a podcast called Machine Learning Cafe, which is more like an in-depth discussion type of podcast, kind of 1 hour long interviews with some experts about their work, which is hopefully close to the state of the art, and we try to deep dive into stuff. So if you want to kind of put something semi-entertaining, I would say, into your ears while you are commuting, then that's that. Yeah, I talked about this, Budapest AI, I talked about Machine Learning Cafe, and one thing that we will do together as a also in-depth type of thing is that there will be a conference called Reinforced Conf that we are kind of co-organizers / we are responsible for getting all the speakers. So we would like to get speakers from pretty big organizations. There were some chief data science of Uber and such kind of people in the previous years when there was a conf. So we would like to reinvigorate that in March.
Next year, just.
Next year.
So that's this year, yeah.
Oh!
Yeah, but
Sorry.
it will be next year, just.
It will be next year.
Yeah.
Sorry, I will have to fix it. And not with the numbers, and please feel free to think about your topics. So there will be, from now on, hopefully every monthly, 2 monthly, there will be a meetup again. There will be hopefully one Christmas edition for December. So anyone feels the power and tries to push an agenda, please reach out to us, and that's that. So with this,
just a sentence about this. So you guys, it's really hard to kind of organize the whole thing. But if there's no speaker, how or what for should you organize it? Yes.
So it's could be some solutions. So for example, not yet. It's a solution which has been implemented.
Sure. Also, there were some practitioner talks also previously, like there was a lady who was speaking about healthcare, like a very specific healthcare problem that they solved. So not just about papers. It's also valid if someone is having an overview of state-of-the-art research. That is cool, but also practitioner talks are very much welcome. So feel free to. That's absolutely. The floor is yours and not mine. So thank you very much. And without further ado, please talk about representation learning.
Thank you, Debbie, for the warm-up. Let's start with the first slide.
The man who's lazy and proud about it.
Title is a little bit complicated. I hope you don't mind it. Alright, so representation learning. I would like to start this very interesting presentation with a very boring definition. So representation is basically encoding important features, important properties of an object, event, or the source. So on the other hand, let's start with something interesting. This poster is a perfect example of representation. I don't know what you think about this shark, but I don't really care about its tail. The most important feature is its mouth, in my opinion, and they did a really good job with this poster. You should note that this representation of the shark is encoding only a small portion of the information about the shark. And it can be really useful because representations so the representations when encoding this small information content, they are really they are really useful because our machine learning algorithms are really sensitive to input size. So when you have a smaller size representation of the whole information, you can make your machine learning algorithms more efficient. All right. So
it's like the shark is a very complex creature, but for this monster you need to kind of just see the tooth, the teeth.
Yes, that's the most important feature for this task. All right. So representations come in all shapes and sizes. On one end of the scale, you have feature-rich representations like an image. It's easy to imagine that you can compress this to a more compact representation which you can use. On the other scale, you have words, for example. And if you imagine that you meet a guy who never seen a shark or never heard about a shark, this word, this representation of the shark would mean nothing to him. So he needs some context for this. So representations come in all sizes and shapes. You should remember that. And then let's switch to feature engineering, which is, I believe, the beginning of this representation learning history. Because feature engineering is basically the process of encoding our domain knowledge to create a more compact and useful feature for our machine learning algorithms. These feature engineerings have two main types. First, when you are transforming your feature to encode this image. This toy problem is actually a quite useful presentation tool. On TensorFlow playground, you can test really small neural networks, and it plots the decision boundary for your classification or regression problem. This is a classification problem. You have points from two spiral, and the neural network have to decide which point goes where. The same network, this same small network works much better if you also include the transformed input. This sinus of x and sinus of y. I think it's easy to see why, because of the shape of the spirals. Of course, it's just a toy problem. I just wanted to give you some visual idea about overall the representation. The other type of problems when you are encoding your knowledge by combining features. Let's say we have this also toy problem. You have an amusement park and you want to position 10 or 20 food truck. And you want to predict the turnover. You can try to one-hot encode your trucks, which would probably work. However, this representation of the trucks, this one-hot encoded representation, is not ideal. It's easy to see that by giving more information about the trucks, let's say the closest shop, you can create much more interesting representation for your trucks. Of course, over a certain complexity, it starts to get harder and harder. Because maybe the closest shop is useful information, but what about the second closest shop? Is that important information? I don't know. So over a certain complexity, we need some help. So we can use algorithms for this. For example, for images, which is a quite complex information, in the early 2000s, before this current AI revolution of 2010. They started to create image recognition algorithms which mined features automatically from reference images and use these features to and they were looking for these features on other images. But this is feature mining, but it's getting closer to current representation learning solutions. What you can see here is the SIFT algorithm, if you're interested. Alright, so current day representational learning. It has two main branch, I would say, supervised solutions and unsupervised solutions. I think unsupervised solutions are much more interesting because no one likes to label data. It's costly and time consuming. The unsupervised algorithms have many variants. You can see a few here, but I am going to concentrate on the deep learning solutions. I hope everyone is here for this.
May I have a question?
Yes.
Why we start to talk about representation learning today, knowing that those techniques, especially in the middle up, quite long time exist. So those we know that before, we used that a lot, but we didn't call them representation learning. Why we start now to look at this problem in a different angle, let's say?
Well, it's a good question. I would say with the advent of deep learning solutions, with the higher amount of data and processing power, I think this deep learning branch grows so much that it acquired a new name.
So you say that we did it before, we just didn't call it on its name?
Yes.
Because we didn't realize that we are actually doing that, because we couldn't do that on that extent,
Yes.
that we can call it, okay.
So the feature mining algorithms were actually borderline representation learning algorithms, in my opinion.
So, may I say something about this? I'm not very knowledgeable about the history of this term, but I was pretty surprised that Inton and Co, so those people who started this whole deep learning, came up with the backpropagation algorithm and so on. Even in the 90s, I read papers where they were using this terminology.
Really?
Yeah, the neural networks, they do learn representations. This is representation learning. So maybe this was just a minority tradition, which now is becoming mainstream. But it was already there.
I think it stems from the early perceptron, like the single perceptron with the linear. In the Stanford, they did this kind of studies in the 70s.
Maybe. Can easily be the case.
Possible. The name was already used, but not mainstream. I think that's the best description.
I mean, also it's rather arguable that the mining techniques that you were referring to, or some other techniques that are written there, are more instance-based. So they are not learning a generalized representation that much as some kind of pretty close to the input level features or instances of co-occurrences or something like that. So I think, though it's not easy to be quantified, but there is a substantial difference between a deep representation, like a strong functional transformation of an input, versus a small chunk of the input that I memorize as a feature. So I think there is something to be found there.
Yes, I think you are quite correct. For example, for image recognition tasks, the low-level primitives are pretty much shared between all images, but higher level features are accessible through deep learning.
Okay.
So, just a quick supervised learning example. where is our representation? Usually we are looking for the representation right before the output of the neural network. So the last layer before the output. And I am going to give an example why. Sorry. I am going to give you an example a little bit later. But first, let's speak about how we evaluate these representations. There are three main solutions which you can frequently find in papers and articles and stuff like that. The first is the linear probe kind of solution. This means that if you have a classification task, you take the representation and learn a logistic regression algorithm. If you have a regression task, then you are doing a linear regression on the representation. And based on the results, you can decide if your representation is good for your task or not so good. This is the first one. And the second one is a more recent development. This central kernel alignment type of solution, which is basically really simple. You take the representation of a few samples or lots of samples, and you are measuring the similarity between these representations. So you basically get a representation matrix, and then you can compare this matrix, distance matrix, to other representation distance matrices. For example, if you are using this for a classification task, you have a one-hot encoded label. You can create this distance matrix. It is going to be very orthogonal, but still it's going to be a distance matrix, and you can compare this with your representation's distance matrix with this central kernel alignment. This seems a bit counterintuitive. It's not ideal for comparing the output, but for example, if you want to compare the representation of different layers, then it's much more useful, because it gives you an idea about the structure of the representation. Just a quick example. If you have a representation of a cat, a lion and a tiger, these representations should have a very close similarity to each other. So your distance matrix should have a nice rectangle which is full of ones. I hope you understand. Alright, I am going to speak about this later, because we are going to use this metric to describe how similar is the representation of supervised and unsupervised representations. Alright, and the third version is my favorite. You just take your representation, put it into a dimension reduction method like UMAP or ECA, and then plot it. Then label the points according to their class or value, and then you can use your most advanced pattern recognition software here to find out if your representation is good for your task or not. And now I give you that example what I promised you earlier. Yes, please.
Just one question is that what is central kernel alignment, what you told to me, this is like remembers me like when we are having this facial recognition and many face-based face detection, face tracking, whatever, many solutions, and this is well researched over quite many years. But it's strange that basically the general idea is currently in deep learning, even with these solutions, that we are just learning inside the deep learning networks basically the distance from the average face. So which is like, there is one average human face, which is not female, male, whatever, and all the solutions basically just learning the distances when they are getting the representation during the training for any solutions, and that's why they are working very well. At least that's not my idea, but I heard about this, like why this is like so well-known solution, and like many solutions are out there, and probably this is a good example for this kernel alignment, because basically just like the average face is like an average, like the basic kernel, and you are just basically learning inside a deep learning network the distances, like when you are training with different examples, something like this.
Well, if you think about that, that's also the representations. You are creating a representation with an encoder, and compare that representation to another representation, another facing representation, and give a distance metric. However, you are using the same encoder in this case. And central kernel alignment have one really useful property. I understand the pipe papers correctly, that they can handle very well scale differences. So if you take representation from two differently trained networks, they might have different scale. Let's say there is a multiplier of 5 for each representational value in one network. This central kernel alignment should be able to find similarity even with this difference. I hope you answered your question. Alright, so I trained a neural network on the brainwaves of alcoholists and non-alcoholist people. It's also a toy problem.
Since they are so
Was it the balance? Was it the balance rate?
Yes, actually it was.
And it's a self-reflection data set?
No.
Are we in there?
No, I'm not. Do you want to? In which group?
It's in the representation, then.
So it was a deep convolutional network, 10 or 11 layer, if I'm correct. And I took the output of each layer for the whole validation set, and they used UMAP, this dimensionality reduction method, to compress this representation into 2 dimensions. So for each sample, from each brainwave sample, we have 1 point here. And they are colored by darkness. Actually, I'm not sure which is which one. It doesn't really matter there.
It's politically correct now today.
So,
No one was harmed during this experiment, so.
yeah. On the upper left corner, you can see the 6th layer from the output. So the information travels 6 more layers until the output. And you can see that the representation is not really discriminating well for this task, this classification task. However, as we go closer to the output, the network builds more complex representations. It starts to discriminate better and better. And at the last layer, which is actually a density, you can see that we have almost perfect separation. So that's why we usually use the last layer before the output.
Sorry for that. Have you used like a preprocess EEG data, or is just a raw EEG time series that you flip from number?
It was just scaled between 0 and 1.
And that's also it's lower the noise and every artifact taken care of by the process.
Well, probably the first few layers probably filtered the noise, found the primitives, and then they started to build higher and higher level representations.
Did the Fourier for you?
Yes.
But the input was some kind of image of the EEG signal, or this is like a float number?
It's like measurement. Like
It was, I believe, 32 or 69 channel time series and 255, 56 time point, if I'm correct. I don't know about the sampling rate, but
Yeah, and you trained this from scratch, right? So this is not
Yes,
a
yes,
fine
I did.
network.
well, actually, it was just for presentation purposes. It's also to a dataset from Graphical. Yes.
So the autoencoders by itself doesn't do that. That basically reducing noise, build up the features, reducing
I am
noise.
going to talk about that.
Sorry, then I don't want to.
Yeah. So the main part of the presentation is coming right now.
By the way, the same structure was used on non-toy data set. Not particularly this architecture, but we work with the rodent EEG data.
Yes, but that pharmacology.
Yeah, we are not allowed to show the rodent EEGs, so stick with alcoholics.
Yeah, actually, it's the same algorithm.
Same algorithm, but
Same network.
So basically, this was a nice example where you have a supervised signal kind of driving the whole
Yes, exactly.
representation.
Yes, exactly. So, I am going to talk about the unsupervised deep learning branch. Actually, this branch is also called self-supervising. For some kind of reason, they really like to confuse us with all kinds of naming conventions. And I am going to talk about a few main tasks, which is unsupervised method. One of these are the autoencoder. So, one of the often used unsupervised tasks is when you want to predict the next step, next sample, in a time series or in a natural language example. So the idea here is that you can only predict the next step if you understand the underlying system which generates this sample. And by learning this, you learn basically everything. There are quite a few famous examples for this. For example, GPT-3 also uses this. I don't really want to go into that. It's a really good representation learning method. The representation here is also right before our output layer. And what is really interesting that it can be also used for image data. I'm sure many of you have already seen this image GPT. They are basically converted 2D images to a one-dimensional series, and they just ask the network to complete the images. It's quite funny, in my opinion, and it works quite well. And what is really interesting, image GPT also thinks the most important part of the shark is its mouth. Just saying. Alright. Another type of unsupervised task, which I or destroy restore is basically very simple. You remove information from your input sample somehow and ask the network to complete it. For example, if you have a sentence, you remove a word and ask the network to find that word which is missing. Or you take an image and convert it to grayscale and ask the network to find out which is the original RGB image. So this is the sample manipulation type of destroy restore task. There is another one, which is the autoencoder. Here we destroy the information by forcing it through a bottleneck. So yes.
As an addition, it's for the autoencoders, it's quite important that just to compare to the previous picture where we took out information. Now we need to add the initial Gaussian noise to induce.
That is one variation of.
This is not variation of autoencoder.
That's one variation of.
Autoencoder.
So there are normal autoencoders which don't have this resampling phase. But yes, variational autoencoders are usually better. They have quite a few upside compared to the normal autoencoder. For example, your representational space is much smoother.
Much what, sorry?
Smooth. So for the autoencoder task, your input is your original sample, and the output should be this sample. The network should restore it perfectly, which doesn't sound too hard, but if you introduce informational bottleneck, few neuron wide dense layer or few channel deep convolutional filter or something like that, then you destroy information after this encoder phase, and the decoder has to work really hard to restore it. In this case, the representation is in the bottleneck. It's important to keep it in mind. Another unsupervised method is actually contrastive learning is not an unsupervised method, but it can be used as an unsupervised method. So CLR is for learning representations of images. Actually, contrastive methods compare two images. They are encoding these images with the same network, and then they compare the representations. So the unsupervised part of this is that you don't have labels. You take the original samples, apply really heavy augmentation, and use these as positive samples. So let's say we have the original image and the Gaussian blurred image, and we give it the network, and we expect it to create the same representation for this, or a very similar one. So the network learns the general features of the dog, so it creates a good representation for it. The negative sample is just any negative sample. Take a dog and a cat, and you are done. So we are going to come back to this method a little bit later. Another unsupervised task, which is quite not new, but
But it is. Pretty recent.
Yes, pretty recent. Yes, that's say, there are varied tasks. Varied tasks. So let's take clip. OpenAI trained the clip on pairs of images found online and text of the image.
Text captions.
Text captions. Yes, correct. And the task was to find out of 32,000 something caption, the right caption for the image. And actually they created really good representation with this kind of task. You can see here that the upper two clip version beat most of the image recognition baselines on zero-shot tasks.
By the way, please bear in mind that the captions are noisy. It's not that the captions must be perfect. It chooses one more, the least bad captions, so to say.
Yes.
Sorry, what is the x-axis? I don't see.
X-axis is the forward task, so require processing power for inference. Alright, so what is
So
the
where do the captions come from?
They scraped from the web and there was an image and an image caption which hopefully really described the image or not.
This is one data point, like an image and the actual caption.
And then you input the image and you expect it to rank the captions and take the most similar, the thing that was near to the image when you scraped it.
What is really hard here, that the captions are changing. So it's not a simple classification task.
Yeah, but so this is what I didn't understand, that the alternatives are just like negative samples.
Other
captions.
captions.
Okay, I understand. And how many alternatives are? Approximately
32,000 something. Some
like all.
Sample
and you sample.
I don't remember like what batch size they did or what was the sampling there.
The x-axis is the computation, use of computation, right? So there it's taking care of the slope of how the solution is struggling to compute the
just a moment. So it's about zero-shot task. So they train this network, took the representation, and used a linear probe, which we told about, logistic regression, to make classification of random samples.
Unseen samples.
Yes. So the representation was what they learned was really good. Actually, they were so good that they beat the models which were trained for classification. So that's what you can see on the y-axis, this zero-shot lunar probe accuracy, and on the x-axis you see the model, the required power for inference, which basically means the model size. All right. Another really funny and one of my favorite unsupervised tasks is the Jigsaw Puzzle. The idea here is you take patches and ask the network to find out where are these patches compared to each other. It is a quite crazy idea, but it works really well. And since the visual transformers recently became the state of the art in vision, they started to investigate how they can work so well on images. And one of the papers, which are in the links at the end of the presentation, they investigated this and they found that the patch embedding method of the vision transformers are a huge part of their power. And you are doing a very similar thing here with this Jigsaw Puzzle type of task. That's quite interesting in my opinion. Just keep in mind. And I think we are at the last unsupervised task. I hope not everyone is bored. Okay. So, Dino is a Facebook trained algorithm, and has a really nice representation. But why is it here? Because of the emergent properties inside its vision transformer. So, in transformers, self-attention heads have two-dimensional representations, and in these two-dimensional representations, an emerging property was created somehow by this unsupervised task, which is this emergent property is that it segments objects pretty well, surprisingly. Of course, these are the cherry-picked examples from their paper, so it's not so perfect in real life, but at the end of the paper, you can find other examples, and they are still pretty good, surprisingly. So this is why I used Dino as an example, because you can basically have a zero-shot segmentation method with this, or the basics of your segmentation model really easily. The train model is available online. You can download it, you can play with it. It's quite easy.
What is the self-supervised task?
Oh, right, self-distillation. Self-distillation is a little bit of a tricky method where you are usually forcing the network to okay, so distillation, the usual knowledge distillation methods work with the teacher and the student network. The teacher network trains the student network, which is usually much similar. In self-distillation, it works very differently. However, in the Dino paper, they said they think they have a self-distillation kind of task somehow. The details are a little bit of black magic for me, I will be honest with you, but the idea is that they are somehow forcing shallower transformer layers to learn from the whole network.
What is the task here for this Dino? So it's getting an image and it's saying those categories. What was first shown? I mean, before this, there were all these categories.
It's unsupervised learning. There are no categories.
Ah, yeah.
They have just the images, and the task is to have the same representation of from the whole network and the shallower subnetworks. It's quite tricky and it's like black magic in my opinion, but if it works, we can use it.
Münchhausen style, like it bootstraps itself out of the sweat somehow.
Well, actually, maybe 1 or 2 years later in a white paper, maybe they will find out why it works well, and then we can use it perfectly.
Why do we call it distillation? Okay, normally I use this word for pretty different meaning, which I like, but
so the original knowledge distillation networks are using this in the sense that from a huge parameter set of a network, they distill it to a few important parameters.
Originally, it was a Hinton paper that is pretty old, by the way, that came up with the idea that if you train a large enough network and you take the output of, like you have a supervised task, you train a big network on it, nothing fancy. But for the input, for the target of the smaller network that you initialize, you don't take just the class labels, but you take the output of the last to previous to last layer of the big network as a target, and that was kind of the original idea of take the knowledge from that was processed by the big network and show that knowledge to a smaller network, and that kind of bootstraps the learning procedure of the smaller network, because the targets of the smaller networks are not one-hot encoded big one-hot encoded vectors, but they are more semantic or more meaningful vectors.
Even the probabilistic output is enough.
Or the probability, maybe
something more fine-grained, which tells you more about the behavior, about the large network, about the behavior of the large network.
Yeah, you're right, because they didn't take the last and previous, but they took the softmax. Sure.
Yeah.
But that was kind of distilling the knowledge of the big network to the small, but then comes this I don't know, black magic trickery of, and you do it in one network somehow between the layers. Of thinking that the shallower layers are representing a different network, which is the small one, and somehow you just try to conform the later layers representation to the previous ones, which shouldn't work, but it does. So, I don't know.
It seems like if you have enough data, it works. Alright, so, I see. This is the end of the boring part. So, the question is that we told about supervised representations and unsupervised representation learning methods. Is the representation the same? It's a really interesting question, in my opinion. And there is a recent paper which investigated this. So on the left side, you can see the linear probe for these representations. And on the right side, you can see the central kernel alignment values with the classes. And they compared the SIM CLR unsupervised learning method to another supervised learning method. The encoding part of the network was a ResNet network stock standard. And what they learned in this paper is that in the first few layers, the learned primitives, so edges, simple patterns, are pretty much the same, and they have the same discriminative power. In the middle layers, the SIM CLR unsupervised method builds up a strong representation regarding the classes somehow. And in the later layers, both network fits to its own task. So in case of the unsupervised learning method, it fits to be augmentation invariant. The supervised method fits to classify the samples. And yes. What was really interesting that the representations in the residual part of the ResNets are similar. However, the non-residual parts are very dissimilar. This is interesting because it depends, it matters when from where you are taking your representation. If you are taking your representation from the residual part of the ResNet, then you will have a much more similar representation to this.
By the way, I mean, this is interesting that they did this with ResNets, whereby ResNets are having this feature of gradually building up a representation. You know, that the original idea of ResNet was just exactly that. So I don't know if they managed to measure the fact that it is a ResNet, or did they measure something really kind of arguable.
Good question. There was.
Yeah, I mean, they didn't try to do anything against it.
Sure. Sorry, but the residual part of similarity is not coming from the guy who's taking the picture. Like every picture is taken almost at the same point. Like if you would take a closer picture from an animal and a more further picture, the residual is still similar.
I think the residual part they were mentioned is the inside of the block, not the skip connection. Or what do you mean?
So inside of the feature.
Yes.
Okay.
Yeah, I mean, the residual block is basically a dual channel processing mode in which certain, like there is a possibility to pass through information that came into the block, and then you are just kind of gradually refining some of this information and feeding it back potentially. And I think the original idea of what a ResNet, but Andras may correct me, is that it's basically in the beginning, everything is basically just passing through. And it acts like a shallow network and gradually learns to refine its
within a module.
Within a module.
So their exact wording was the block interior representations are similar. However, after adding the residual, they were more dissimilar. Probably because of the simple augmentations. Alright, so let's talk a little bit about transfer learning and its weird connection to representation learning. So, in transfer learning, we are often training the network to do one task and cut down its classifier layer and attach another classifier or something. And then we train these new models again on a new task, and we expect it to perform better. However, the already trained models, the pre-trained models, often are quite huge. So we are freezing the few first or many few first layer, and actually that means that we have a pre-trained model which creates a representation for us, and then we are using this representation to train a smaller model. And I find it quite fascinating that we have so many applications where we have this kind of shared features. It works really well with image recognition tasks, and
is it only the classifier what we put on?
sorry?
Is it only the classifier what we put on the tail?
You can put
No, I mean,
anything.
you said that, you mentioned that we are going to use the representation from the original network.
Yes.
Does it mean that we take it ready? Or do we still shape it on?
There is a thing called gradual unfreezing, which is a kind of default technique. UML fit people. So I think it was Ruder and Co. who started this thing, in the sense of you take a model, you freeze it for a while, put like 1 or 2 layers of the specific thing on top of it, but because it's randomly initialized, if you would let the gradients flow, then you would destroy everything because of backdrop. Okay. So you freeze it up until a point, and then like for an epoch or 2, you only train the top part, and then you gradually unfreeze more and more layers in the beginning to do the fine-tuning.
Okay,
final,
this is
like
I'm asking.
10th epoch or
Okay, this is I'm asking that
already you have.
you still shape that representation.
Yeah,
later
well,
on?
not necessarily, but many times you do. In these big
okay.
BERT type of models, it's so expensive to do a full training that you don't even unfreeze.
Okay.
Because like, who has the computation for that?
On Amazon has, but you don't have the money for it.
I'm not Amazon, you know.
Yeah, what I find funny is that in a sense this totally like typical thing when you just put a very shallow network on top of pre-trained stuff and
Basically, a
now
linear probe.
this is a linear, yeah, this is
a linear
exactly, this is
probe.
basically just a linear probe.
Which means
Using this terminology.
yes, if you have one layer, then it's basically a linear probe. Yeah. But linear regression is less costly.
So one more question. So how you can decide how many layers you should draw from the end of the network? So only the classification layer or a few more, or it depends?
Trial and error.
Ah, okay.
Or you can use
Linear probes.
linear probes to decide where you want to have a workout. So, as you can see, there is a jump in the discriminating power of the unsupervised network at a certain point. I would say you freeze the layers right after that point and train the rest. I would do that. But of course, trial and error.
How do you know where to cut?
Sorry?
How do you know where to cut?
Sorry, I don't understand.
How do you decide where to cut, where to freeze?
So, like I said, if you are doing a linear probe layer by layer, you will see where the discriminating power of the already trained network start to increase.
You say you do it all the way and then you decide.
Yes.
Okay.
Yes,
Okay.
That's one method.
Okay.
There are some quite fancy like variations of this.
Yeah, differential learning rates and whatnot.
Some people just try to take a linear combination with learned weights of the layers, so just combining the representations.
So the soft non-freezing version is a thing called differential learning rates, meaning that you just do layer-wise a decaying learning rate and don't freeze everything, just let backprop be very subtle in the beginning and very gross in the end. That's
Fade it all.
Alright, and this is pretty much my last slide. You survived. So it's about fractal pre-training. It's a quite recent paper. So as we all know that fractals are all around us in nature. So why not train our image recognition model on the generated fractals, right? And they found that a model trained on ImageNet and fractals have pretty much the same primitives at the beginning. What is also really interesting that these fractals can be not only self-similar, but can be similar to another fractal. And they decided to create a multi-instance classification where they had to classify not just which was the generative fractal originally, but to which it is also similar to. And actually they are created a much better model. Actually, I don't have the results here, but from this multitask unsupervised, actually it was a supervised task, but with this additional task, they created a much better convolutional filters, which were much more similar to an ImageNet trained. I just find it interesting. In unsupervised learning, they are also starting to test how multitask unsupervised learning works, and is it better or not. It will be an interesting development in the next few years. Alright, thank you very much. If you have questions, I would say, after the workshop.
Yeah, I think the questions are as follows. Now it's 7:40. Let's maybe take a shortish break after the 7:50, and then we will start with the next presentation. Discussions and questions and whatnot, just feel free to shoot at this guy because that's why he did the whole thing.
And I have the links to the papers and the GitHub repos if you are interested.
Yeah, so we will send it out. Please very warmly welcome Balázs, who is in a very compressed form, as a small icon up there. So he's now there as an icon, but a visible icon, and he's waving. So please warmly welcome him, and let's continue to dive into quantum machine learning, which is again mind-boggling stuff that is even worse than representation learning, we hope. The floor is yours.
Hello and welcome.
Yeah.
We can hear you loud and clear.
Okay, cool, thanks. Let me know if something changes. I'm Balázs Bódi, and I'd like to talk to you about quantum machine learning. I mean, most of the talk will be the basic blocks of like quantum computation and stuff. I brought you a quote that I really like from Richard P. Feynman, who thought that he thinks that nobody understands quantum mechanics. I think this is a good start for anyone who haven't met quantum mechanics really deeply yet. So, some outline. I'll try to talk some kind of past, present, future method as a timeline. So in the beginning there will be some physics. After there will be some motivation and where are we today, and then the quantum machine learning part will be the future part mostly. So about physics class, some people might already heard that from physics teachers on physics class. If something is a particle or a wave, well, from a human perspective, this question should depend on the experiment, on the viewer, somewhat. On the top right, can you see my mouse cursor?
Yes, we do.
Cool. So the single slit pattern is happening. Oh, there's this double slit experiment. I think this is a very basic thing in quantum mechanics. So let's imagine some kind of beam gun. This can be electrons, like the label says, or this can be photons, or even larger particles. So as a first idea, let's cover one of the slits. So we have only one slit. This should give something like the single slit pattern here. So there is one spot, maybe a bit wider in a vertical way, but something like this. What happens when we uncover the other one? There are fringes or stripes appearing on the screen, which is not really simple to understand with classical knowledge, classical physics knowledge. And the idea behind it is that the particles are interfering. So they meet and they add together in amplitude, and what we see on the screen is already the intensity, so the square of this amplitude. if you have seen waves before, this is just the same idea that somewhere the waves coming from this slit and this slit are constructively and destructively interfering. So where they meet constructively, there's a visible stripe on the screen, and where there's nothing, then they are destructively interfering, so they are canceling each other. To put a trick on this experiment would be to put a detector, some kind of particle detector on one of the slits, so it can detect if there's something getting through or not. And the thing is that if we measure on which slit the particle gets through, we get back the single slit pattern in double. So the original concept of what we would see with the classical knowledge. So two of these slits, one behind each slit. So one of these patterns behind each slit. To put another trick, it's possible to destroy this kind of information before anybody's seeing it, which means that we destroyed the evidence of detecting where the electron went. So this gives back the double slit pattern, which is, I think, really interesting. I didn't tell before, but it's possible to do this with single particles. So there's only one particle leaving this gun, and it's going through both of the slits and interfering with itself, which is kind of strange but interesting. Okay, you need to repeat this experiment many times to see the statistics on the screen with these stripes, but this is the statistics of single particles with a double slit. To ask the question again, if it's a particle or a wave, there's another answer to this question, because the model behind the formalism doesn't really care about labeling. So in either way, the maths behind will describe what's happening. Okay, somebody with physics knowledge could argue with me, because there are some equations or formulas like the Heisenberg's uncertainty, where if one of the sigmas is much larger than the other one, it can show that we are closer to a particle or a wave, but still this is just labeling again. Okay, knowing this, let's go for quantum computing, quantum informatics. What's a quantum bit? So moving from classical bits to quantum bits, a quantum bit can take many different values. They usually present it as a surface of a sphere, of a unit sphere. And this psi can go anywhere on this sphere. You can label it with angles if you want. So here, let's define how would an algorithm, a program, work on a quantum computer. There's three parts, basically. There's single qubit operators, which are rotations around any axis. The main operations are rotations around the coordinate system axis, but with some geometrical knowledge, it's quite simple to realize that using all the three axes, I mean rotations around all the three, any axis, any rotations can be made out of these three. doing after each other. So, and the next operation would be measurement. What happens when we measure? Measurement, the basic idea of measurement is to find out if this psi wants to show itself as a zero state, which is z plus, or a state 1, which is z minus on the other side. This psi is already formulated here like this. So this is the 0 above and the 1 below. And alpha and beta are complex numbers with this normalization. So they are normalized the absolute square values to 1. And these alpha absolute square and beta absolute square are actually the probabilities of measuring 0 and 1. So even if our qubit is somewhere really close to state 0, somewhere here, it's possible to measure it as qubit 1 with a really small probability, but it's still possible. There's also one important thing here is that today's quantum computers are said to be able to measure only in this space. So it's always 0 or 1. It's pretty simple to see that it's if we can rotate, we can measure already in y or x or any kind of axis. Because first we rotate and then we measure in z. If we want to measure in this y, then we first rotate in around x with 90 degrees, and then we just measure z, and that's equivalent if we measured it in y. All the quantum algorithms and quantum computers initialize the quantum bits as zero state, so all of them start here. The third thing about quantum algorithm is entanglement. The operation is called controlled operations that needs to be used for entanglement, and it just an XOR operation. It's important to see that both here and both here, there's another thing, another output, because all the quantum operations are reversible. So, and reversibility needs two outputs if there were two inputs. And as you can see, if we do this again with this as input, it's reversed. So just inverse of itself, this operation. So entanglement is when we put two or even more quantum bits in a coherent state. This is really useful, and this is actually where the fun starts in quantum computation, because it's useful for a lot of things, and and this is how we can scan big spaces of fields of data. We'll see in a few slides. So one application would be quantum teleportation. This doesn't mean physical teleportation, maybe matter teleportation, but teleportation of information. And as you can realize quite fast that this could be used for quantum cryptography. So just transferring data from one spot to another totally secretly. It's not possible to eavesdrop by any means. So the next part is about what exactly $10 million quantum computer is good for. Oh, when I talk people about quantum computation and quantum machine learning, they keep asking me this question: if quantum computers are just super fast computers. And there's a quick answer for that. It's no, they're not. It's a complete different logic how they work. With all these strange quantum world behind. So what's actually happening in the background in a quantum experiment? You've seen this image before, but to be honest, that's not only happening that the electron is going through both slits. If just this is not a box that it's totally closed with only these two slits, then the electron goes around this plate, both sides, above and below, and there are versions when the electron leaves the atmosphere, goes around the moon, comes back and hits the screen with a really, really low amplitude. So we don't really detect that, but everything, every possible path is counted on the screen that you can imagine. What is this good for? I hear someone from the first row saying combinatorical optimization, and well, yes. So any kind of extreme can be searched. So there's like a plane, I mean a 3D space or any kind of multi-dimension configurational space that we can search like minima. Let's imagine some small magnets. Let's call them spins, to be exact or simple. These spins can look up and they can look down, so they can be flipped with these two states. And let's put them in a grid where we can put many of these. And you can already see that this is a discrete configuration space of many dimensions. This is a and let's imagine that one of these and all of these spins are just qubits. So when we leave them to go freely, they can take any kind of directions like before. But when we measure, they take the red or the blue way, looking up or down. Most of these models are about local connections. So we put a function of all these n variables of 0 and 1 and try to find the minimum of all of these on the nth states. As you can see, this is already an exponential problem. So with classical computation, this is just impossible to find the global minima. Okay, there are heuristics and a lot of tricky ways how to get forward, but there's no sure method and no proof that we found the global minimum or maximum. There are, in this combinatorial optimization, there are a lot of tasks and ideas. I took this list from Wikipedia. You can see here the traveling salesman, which is probably one of the most popular of these. And I took one that wasn't even on the list called Maximum Cut, where the task is to cut a graph in half. Okay, this is a really simple graph with these 3 nodes, but you can imagine with a couple hundreds, thousands, millions of nodes, and we want to cut it in half. All the edges have weights, and the question is, how can we cut it in half so the weights of that were cut, we sum it up and to be maximum of all possible solutions. And it's also this kind of MP-Hertz problem. Okay, what about RSA? In the beginning of quantum computation, many people were dreaming about just, cracking RSA and break the banking system as we know it. This is just another NP-complete problem where we need to factorize a number into 2 primes. So we want to find n, where n is the product of p and q primes. So for RSA 2048, this is the biggest number. I took this also from Wikipedia. Actually, I'm not a security expert, so I was, when I looked it up, I was wondering if it's the 2048 bits is for P and Q or N, and this is actually N. And I liked this number so much that I wanted to show you because it's really a huge number. And the question how a quantum computer would solve this, short algorithm works and would need like 4,000 qubits, logical qubits to do this. And also there's a bounty for this number. If you want to break it up into 2 primes, it's like 200,000 US dollars or something like that. Okay, what about quantum neural networks? So here you can see a visualization of quantum algorithm. I didn't show you before, but here it is. It has a classical feedback, as you can see here. So it starts with 0 states, as I told before. Here there is encoding. So the input data will need to encode somehow. There's many ideas to encode, and it's already not simple. If you took the basic idea of using bits of numbers, like using 16 qubits for a 16-bit integer, then we would need 16 qubits just for an integer. And that's already quite easy to see that it's a waste of qubits, because all this information can easily go into 1 qubit, but it needs a lot of encoding So it's much harder to encode a lot of data into a qubit. Actually, you can encode much more data. I heard about ideas to put the information of a whole CD into one photon, but it's not really practical. And when you measure it, you can get back only one bit of information from the whole CD, so you cannot get too much out of it. Anyway, here there are a lot of quantum gates, and this is in this neural net example. This is for the calculation of weights. Like you see here, Z and X and Y gates, which are rotations around Z and Y axis. There are C nodes, like control operations here. And after long row of these gates, we can measure the output and use some kind of classical algorithm to feedback and change the parameters here. I've seen something like before for quantum GAN. You might remember these generative adversarial networks where they generated a lot of fake faces. So here we don't have a lot of bits, qubits. So for now, it's about generating probability distributions with low dimensions. Not really useful, but this is what it can do for now. This is, as you can see, a hybrid algorithm. There are a lot of these kind of hybrid algorithms because this part is really hard to do with quantum computer, and it's not practical anyway. So also putting these back here would be some kind of classical thing to do, and it's much simpler to do as a hybrid algorithm. You can already see here the problems when I mentioned them. The first was that encoding is quite hard, but I already told that measurement is also hard, because when you measure with n qubits, the result what you measure, okay, you can see only one measurement here, so you can see the measurement of only this qubit, but in most of the cases you measure more, and this is an interference pattern of all the possible states that we measured. It's 2 on the nth power, so it needs a good choice of putting these gates and operations so that the ones that we want, like the minimum, searching for the minimum, it's with a really high amplitude. So there's only a few with quite high amplitude. So if we run the whole algorithm a few times, probably it shows which states are with higher amplitudes, and well, this is about the choice of the operations. And this is all. It's also really interesting problem how to do these operations to be able to see the results as an actual few amplitudes out of the many. Another problem was that we don't have a lot of quantum bits. State-of-the-art general quantum computer of IBM this year has 65 qubits and 72 connections. The goal is to have more qubits and more connections. If we don't have enough connections, we cannot have entanglement for the whole system. The use of all these quantum bits is still have a meaning that there is an operation with the controlled operations put together where we can swap two qubits, the information of two qubits. So that's how we can use more than what's actually totally connected here. So out of the 65 physical qubits, we can use here like maybe 20, maybe only 12. I haven't tried this computer yet. I tried smaller versions before. Actually, IBM has a cloud that everybody can use freely. Oh, and noise. So there is no such system that is hermetically closed. So this means that even these quantum computers that are in vacuum, in these steel plates inside vacuum, has some interaction with the environment. Physicists usually talk about times. So that time that the quantum bit can keep the information like most of the cases on average. And these time scales are encoded here in these colors as IBM is showing them, and they are measuring these quantum computers frequently to see how they perform, how useful they are, how noisy they are. The problem with noise is about the length of the algorithm. The longer the calculation, the more the gates we use, the more the probability that we'll only get noise in the end. So this is really important to keep the noise as low as possible, have as many qubits as possible with all the connections as possible. And that's why it seems that it's mostly future the quantum machine learning, because what these quantum computers can solve are well outperformed by classic computers. We have many decades of advantage with classical computers. They are really good. That's why quantum computers seem to be really lame, on the other hand. Just getting back to RSA. Shor's algorithm with 4,000 logical qubits would need like 5 million physical qubits, as people thing who know what they are talking about. I have personally no idea about prescaling quantum computers up to 4,000 logical qubits. But well, this is probably possible in 10, maybe 15 years. So don't worry about that the bank system is about to fall apart because somebody builds a quantum computer in their garage and starts, killing all the securities. Some good news about, on the other hand, about quantum computers. I'm pretty sure that you know that machine learning has many ways and not only neural networks. And one of them is called probabilistic graphical models. The basic idea is having directed or undirected graphs which kind of show probabilities, a network of probabilities. So it's kind of random variables as an event. So every node here is kind of a Boolean variable that can be meant as an event. The directed is called Bayes network, and the undirected is called Markov kind of network. These are actually, the idea is really old because Bayes was living like almost 300 years ago and doing his way of probability theory. The problem was that the Bayesian theory is much more complex, computationally complex, so needs much more computation time than the probability theory that we use until today. And just to show you a really simple example, here I was putting some nodes that, okay, let's say that what's the probability of putting food on my table at lunch? There's a possibility that I cook today, so I'm just cooking the lunch and it can get on the table. There's a possibility that I'm ordering something, or also there's a possibility that my mother drops by, she's visiting me and she cooks something for me. And the question would be, in this case, considering that I have something to eat for this lunch, what is the probability that my mom was dropping by? Okay, this is a really simple graph. Again, imagine a graph with thousands, maybe even millions of these nodes, and it can get really complex. The thing about quantum computers is that with classical computers, if you train one of these networks, it's exponentially hard to train these networks. And when you already trained it, it's again computationally expensive to read out the values. That's the main problem about probabilistic graphical models. The good news is that with quantum computers, the readout will be in polynomial time. just as solving RSA and all the NP complete problems. So that's good news. Oh, I forgot something about random. So I told you before on the beginning that measurement is random. But this is actually really random, not only the pseudo-random that we have in our classical computers that's generating our random numbers with really long sequence of numbers, and it looks like random. This, when using quantum computers, this is real random. So this was, if you remember, this 2019 news that about Google's quantum supremacy, which was not really true anyway, because I think they were generating random numbers only. But anybody who heard that news, I mean, most of the people only remember that they did it, and now quantum computers are better than classical ones, and most of the people don't remember the critics that they actually did it, and it was a really specific task, and we are not there yet. So embrace for impact in the next 10-15 years. This will get much better. I'm pretty sure about that. So thank you for your attention. I was using a lot of images from different sources.
Look at Stalmus, you shout at me and I shout at Balázs. So, any questions? Yep.
Okay, so my first question is basically a comparison with the neuromorphic computing and the quantum computers by the possible usage of both. Like
the question, as I interpreted it, was the comparison between neuromorphic computers and quantum computers with respect to their possible usages.
Neuromorphic?
I
think you're talking about spiking neural networks in hardware and these kind of things, or what?
It's the superconduction based computing system.
Okay, superconductivity based neuromorphic computer hardware versus quantum hardware.
Okay. I'm not sure about that because I haven't heard about this. Is this still a classical computer, just with making it faster with the superconductivity?
So it's basically
easier.
So hi Balázs, I'm Bence.
Hi.
So the basic idea is you build up an infrastructure based on your brain in a hardware. So every superconduction will be one neuron. So every superconductive like this vortex, not vortex, current, superconductive current will be one neuron, and all the information, all the communication between these neurons will be based on photons, because the photon interaction of this superconductive current can be easily made the system decay of the energy. So they can use to compute the differences between the decay of the energy in the electron system. And after this can induce another semiconductor which produce minimal amount of photon to induce another neuron, and they can use a chain reaction.
Okay, I get the idea. As I understand it, this is still a classical computer. So this idea creates the actual supercomputer that they are talking about, and it will be much, much faster than our computers these days, but it's still a classical computer, which means that it's still a classical computation, and there are algorithms and problems like, NP-hard that it won't be able to solve after a number of nodes and elements. So yeah, I think it will be much faster than classical computers. I mean, but it's still a classical computer with classical computation, only much faster. But at some point when we will have quantum computers with millions of qubits, like the next, I don't know, 10, 20, maybe 30 years, that will be able to solve problems that this computer won't be able to solve.
Thank you very much.
More questions? Anyone anywhere? Okay, cool. Then I think
there is no more.
Okay, there is a backup question. Okay.
Okay.
There are
actually two. So basically, is there any way to somehow fit a loss function on the gates position, like where the gates are? So there is a factor of the rotation of the angles. There's a factor of the coordinate measurements, and is there any loss function which is built on where these gates are?
Yes, you can practically calculate anything that you can calculate on a classical computer. The only difference is that everything is trickier. So if you need something like a loss function and putting more values together, it's getting more and more complex. So you will need a log sequence of these rotations and C-naught operators and these kind of and measurements in the end.
Okay, thank you. And my last question is that, is it true that the translation is the bottleneck now? Beyond that, there is not enough qubits and connections, that the translation from the quantum space, the information, the quantum state of the information to the real physical space of the information?
It depends on the problem. All of these are problematic. So, okay, for encoding information, we already have a lot of ways. So it's not simple, and probably different tasks would need different solutions for encoding information. But I think, as I see it, it's simpler because it needs to be done once. But if you want to encode a new algorithm for quantum hardware, you need to start from zero. There are always some kind of modules that you can put that, okay, this module would do arcus sinus or something, but after they start to optimize it, it might not be enough. So with the noise, with not enough qubits, we reading out the results, the measurement results in the end, all of them are really serious problems about quantum computation. It's all of them are tricky because the whole quantum world is just completely different than the world of our logic.
Right. So it means that everything is a bottleneck.
Yeah. I think it's the answer of what I told in the beginning, that it depends on the problem. So if you bring a new problem, it might be you might need a new way of encoding information. You might need new operators. The output, as you know, the interference pattern might be completely different from anything else that we've seen before. It might the sequence of operators might be too long, so it might just get lost all the information in noise. Anything can be a bottleneck. I don't think that there's a real answer here without seeing the task.
Okay, thank you.
Thank you very much, Balázs, for being here, wherever here is basically on the screen. Sorry that you couldn't share the vibes here, but I think there is all the connections that you can make to Balázs, so please feel free to ask him questions on other channels, and I think we just click on him, so to let him go. But all in all, we have this space here up until 9 o'clock, so feel free to socialize, fraternize, and enjoy your evening. Thank you very much. And if anyone wants to come and present on the next one, reach out, because we want you to present stuff. Thank you.